Next important thing is that Poisson distribution. First we will understand what is Poisson distribution, Poisson experiments, then we will try to relate this concept with binomial. Okay. So experiments gives numerical values, okay, of a random variable x, the number of outcomes occurring during a given time or interval or in a specified region are Poisson experiments. Okay. The given time interval may be of it can be any length such as minutes, day, week, month, even year also. So for example, what you can say, a Poisson experiment can generate observations for the random variable x representing the number of car passing. For example, you can take number of car passing through the Munda Dam cross. Okay, here we have a Munda Dam cross. Okay, so in that number of cars passing through and how many number of cars are passing through per hour. Okay, this is certain type of problem where this will be distribution will be used, and the number of days college is closed due to heavy rain or some pandemic something in any rainy season, rain is there. Okay, so the specified region could be line segments. So the specified region, okay, will be line segment piece of material also. In such instances, what we can do, x might represent the number of field mice per acre, the number of bacteria in a given culture, the number of typing error per page. So these are plenty of examples. Okay. So a Poisson experiment is derived from Poisson process and Poisson and processes the following properties, okay, and possesses the following properties. What are the properties? Then it will be, so the number of outcomes occurring in the time in one time interval or specified region or specific or space is time independent or independent, we can say, of the number that occur in any other distant time origin. In this sense, we say that Poisson process has no memory. Please understand the concept here. The number of outcomes occurring in one time interval or specified region of space is independent. If it is independent of occurring of time, means if one student has come 10 o'clock, sorry, 10:10, okay, so this is independent of what the number of student is entering the class at 10 o'clock. Okay, so in that case it is not remembering the previous the probability of the previous event occurred. Okay, that's why it is called memoryless property. Sometimes we call memoryless property. So in this sense we say that the Poisson process has no memory. Second thing, the probability that a single outcome will occur during a very short time interval or in a small region is proportional to the length of the time interval or size of the region, and does not depend on the number of outcomes occurring outside the time interval or region. If you are taking a 10 minutes of time interval outside, you are not bothering about. It is not depending on the outside the limit of the time or interval. Okay, so the probability that more than one outcome will occur in such a short time interval or fall in such a small region is negligible. See, the probability that more than one outcome will occur in such a short time. Okay, so if more than one is such a short time of interval, it is, if it is occurring, we are neglecting that one. Okay, we're concentrating on one, and it has a great application in your queuing theory. Okay, where the number of people are coming in a queue and getting service offered, all those things, network problems, okay, like signals one by one, calls are coming, attending, like customer care center, this type of problems are there. Okay, so this is very real life problem where use Poisson process. Further we'll discuss those things, examples. So the number of the number x of outcomes occurring during Poisson experiment is called Poisson random variable, and the distribution is Poisson distribution. Okay, the mean here, if you see, the mean will come, and that will be lambda into t. So what is lambda? Lambda is the rate of occurrence of outcome. Okay, if one student is coming, so what is the rate of student coming per minute, per hour? Okay, like that. So that will call your lambda value. Even there is a process called birth and death process. There also this Poisson process is useful. Okay, birth means success, and the rate of occurrence of birth, childbirth or other things. So it is generally called birth and death process. We'll see if time permit, those things we will discuss. So we'll denote this like P of x. Okay, semicolon lambda t. There, what we are writing P of B of, okay, that binomial theorem B of x comma n comma p. Here the probability will be of x lambda t. Okay, now this thing. Now the formula for that, the probability distribution of the Poisson random variable x representing the number of outcomes occurring in a given time interval or specified region denoted by t is this. This is very important. The formula P of x lambda t will be e to the power minus lambda t to the power x by x factorial. So this will give you see, now distribution means what? X with respect to p, if you find. So if x equal to 0, what is the p value? X equal to 1, what is the p value? X equal to 2, what is the p value? So if you plot it, you will get a curve. Okay, so that will be the distribution. So lambda is the average number of outcome per unit time or per unit distance, per unit area, whatever be the problem required that way. So you can see also a table there. It contains Poisson probability sums. Okay, P of R lambda t, or you can say P of x lambda t if x is varying from 0 to R. Like for x equal to, here I am writing x equal to 0, some value is there, x equal to 1, some value is there, x equal to 2, some value is there. Like if you want to sum of all those up to R, okay, then how to find and how to get from the Poisson probability. So that we are getting, and the lambda t is varying. If lambda t is varying from 0.1 to 18, what will the value? So you can see this value, Poisson probability sum. You see mu is value lambda into t. If lambda into t, lambda t is 0.1 we are taking, so R equal to 0, 0.9048, R equal to 1, 0.9953. Okay, like this. For 0.2 mu value lambda t, what R value you are getting. So this is a standard table you have given that you can use and you can find out. So 0.1, 0.2, 0.3 up to 0.9 it is there, mu value. Then from 1 to 5 it is there, mu value 9.5, 18 up to 18 it is there. Okay. Now we'll see one problem here and we'll use the tabulated value. So during a laboratory experiment, the average number of radioactive particles passing through a counter in 1 millisecond is 4. So 1 millisecond number of radioactive particles, okay, will be 4. That means lambda into t, 4 into 1 will be 4. Mu will be 4, then 4 per millisecond. So using Poisson distribution, what we have next? What is the probability that 6 particles enter the counter in a given millisecond? So 6 particles means x equal to 6 and mu is given 4, that you have to find. So now we have to find P of 6, 4. P of 6, 4 will be this formula, e to the power minus 4 into 4 to the power 6 by 6 factorial. which you can get like this. Similarly, next question, and the value you can get from the table. 10 is the average number of oil tanker arriving each day at a certain port. The facilities at the port can handle at most 15 tankers per day. Okay, each day it is coming. The average 10 average 10 is coming, but at most uh, 15 tankers per day can handle. What is the probability that on a given day tankers have to be turned over? Turned over means more than 15. The probability of x greater than 15 will be what? 1 minus. Always sum of the probability will be 1. So 1 minus probability of x less than equal to 15 if we do. So probability of x less than equal to 15 is this one formula. 10 is the average mu value given. So x that you have to find out at 10, what will be the value? So 0.95 from table you can get this one. So finally 0.0487 you will get the answer. So here one point you can observe that both the mean and variance of the Poisson distribution are lambda t. Okay. So next thing is that relationship and some problems based on the distribution that we are going to discuss, and we are going to discuss this thing next class.